after the East Channel Bridge was replaced to increase its vertical clearance, providing boats with an alternative route between the two sides of Lake Washington. Further west, the Hood Canal Bridge incorporates truss spans for smaller craft, and it has hydraulic lift sections for larger ships. The U.S. Naval Base Kitsap is not far away, so sometimes the bridge even has to open for Navy submarines. These movable spans can raise vertically above the pontoons, while adjacent bridge segments slide back underneath. The system is flexible. One side can be open for tall but narrow vessels, or both for wider ships. But floating bridges don't just have to make room for boats. In a sense, they are boats. Many historical spans literally floated on boats lashed together, and that comes with its own complications. Unlike fixed structures, floating bridges are constantly interacting with water, waves, currents, and sometimes even tides and ice. They're easiest to implement on calm lakes or rivers with minimal flooding, but water is water, and it's a totally different type of engineering when you're not counting on firm ground to keep things in place. We don't just stretch floating bridges across the banks and hope for the best. They're actually moored in place, usually by long cables and anchors, to keep materials from overstressing and prevent movements that would make the roadway uncomfortable or dangerous. Some anchors use massive concrete slabs placed on the lakebed. Others are tied to piles driven deep into the ground. In particularly deep water or soft soil, anchors are lowered to the bottom with water hoses that jet soil away, allowing the anchor to sink deep into the mud. These anchoring systems do double duty, providing both structural integrity and day-to-day safety for drivers. But even with them, floating bridges have some unique challenges. They naturally sit low to the water, which means that in high winds, waves can crash directly onto the roadway, obscuring the visibility and creating serious risks to road users. Motion from waves and wind can also cause the bridge to flex and shift beneath vehicles, especially unnerving for drivers unused to the sensation. In Washington state, all the major floating bridges have been closed at various times due to weather. The DOT enforces wind thresholds for each bridge. If the wind exceeds the threshold, the bridge is closed to traffic. Even if the bridge is structurally sound, these closures reflect the reality that in extreme weather, the bridge itself becomes part of the storm. But we still haven't addressed the floating elephant in the pool here, the concrete pontoons themselves. Floating bridges have traditionally been made of wood or inflatable rubber, which makes sense if you're trying to stay light and portable, but permanent infrastructure demands something more durable. It might seem counterintuitive to build a buoyant structure out of concrete, but it's not as crazy as it sounds. In fact, civil engineering students compete every year in concrete canoe races hosted by the American Society of Civil Engineers. Actually, I was doing a little recreational math to find a way to make this intuitive, and I stumbled upon a fun little fact. If you want to build a neutrally buoyant hollow concrete cube, there's a neat rule of thumb you can use. Just take the wall thickness in inches, and that's your outer dimension in feet. Want 12-inch thick concrete walls? You'll need a roughly 12-foot cube. This is only fun because of the imperial system, obviously. It's less exciting to say that the two dimensions have a roughly linear relationship with a factor of 12, and I guess it's not really that useful, except that it helps visualize just how feasible it is to make concrete float. Of course, real pontoons have to do more than just barely float themselves. They have to carry the weight of a deck and whatever crosses it with an acceptable margin of safety. That means they're built much larger than a neutrally buoyant box, but mass isn't the only issue. Concrete is a reliable material, and if you watch the channel for a while, you know there are a few things you can count on concrete to do, and one of them is to crack. Usually not a big deal for a lot of structures, but that's a pretty big problem if you're trying to keep water out of a pontoon. Designers put enormous effort into preventing leaks. Modern pontoons are subdivided into sealed chambers. Watertight doors are installed between the chambers so they can still be accessed and inspected. Leak detection systems provide early warnings if anything goes wrong, and piping is pre-installed with pumps on standby, so if a leak develops, the chambers can be pumped dry before disaster strikes. The concrete recipe itself gets extra attention. Specialized